Hi folks, welcome to your Precalc 12B video of the day. I don't know, I guess I'm not doing them every day. So this one is on limits that involve infinity. Sometimes I'll call them infinite limits, but it's not necessarily the limit that is infinite. The best way to describe it would probably be to say that it is limits involving infinity. So, first of all, what is infinity? Infinity is kind of a funky symbol that we are all really comfortable with, but we shouldn't be probably as much as we are because it is not a part of the real number system. So you can't just use it in statements and equations the way that you can a lot of the other symbols that we're used to, whether they be numbers or special symbols for irrational numbers like pi and e. In the case of infinity, it is an idea or concept that allows us to describe really something that's tied more into limits than anything else that we've seen so far. So it's a behavior. Now, we're going to take a look at two different types of limits today. So the first one over on the left, with an extra space in there, no, I guess it's not, is the idea that we have limits that have infinite values that we approach. So again, there's no such thing as a real number value that's infinite, but the idea of allowing a limit to go as far out as you can describe is actually pretty useful and pretty helpful. So in this particular case, we have the limit as x is approaching infinity of f of x, or the limit as x is approaching negative infinity of f of x. So you can think about that basically as saying, if you were to go out as far as you can along the right-hand side of the number line, what would happen to this function? If you go out as far as you can to the left-hand side along the number line of this function, what happens out there? Those are two questions that we'll try to answer for a few different types of functions today, and that is one of the types of limits that involve infinity. The other type of limit that involves infinity that we're going to look at is when you approach a finite value somewhere in the middle, but the behavior around that finite value is infinite. So what ends up happening is the numbers just get so ridiculously large in positive or so ridiculously large in negative that there's no number that can properly describe what you reach. Instead, it's more this idea that it just keeps going and going and going. And we denote that with either a positive infinity or a negative infinity, depending on whether you're on the positive side of your number line or your negative side of your number line. All right, so we're going to start off with the first group, which is what happens in some cases where the limit itself, the value that you're approaching, is infinite. All right, so we're going to do some real simple ones just to start things off. So that first one is the limit as x approaches infinity of the number 5. Okay, so as x approaches infinity, 5 approaches 5. Okay, that's good. So it stays as a 5 because there's no x here to change at all. So it just kind of stays at that 5. So congratulations, you have evaluated an infinite limit. Next up, or a limit involving infinity. As x approaches negative infinity of 5x. Now, this one there is an x, and that x is going to get close to or approach the value of negative infinity. 5 times negative infinity, as you can imagine, makes it get bigger faster, multiplying it by 5, but it doesn't change the sign, and it doesn't change the fact that it's going to end up becoming indescribably large. So this is where, depending on the textbook or the person, you may see a little bit of disagreement as to what we should put in a particular case like this. So this limit is getting, I'll write it down, is equal to negative infinity. I don't like that personally, but a lot of textbooks do. I don't just like it because my infinity is really poor there. I don't know, I'm not very good at it apparently. So the idea is that we are saying that the limit is equal to, This is the part that I have a bit of an issue with. Equal to or is negative infinity. And negative infinity is more of a behavior or concept than a real number from what we had just said. So this is kind of weird to say that the limit is actually just equal to a negative idea, yes, or a negative infinity. Lots of textbooks will say that that's the appropriate answer. I have seen some that will say DNE does not exist because there's no real number that exists to describe that. But by far the more descriptive of the two is to say that it's negative infinity, because it tells somebody not only do you know that it's not a real number, but you know it's the not real number that goes in the negative direction and it becomes very, very large. So I understand why you would want to write down the negative infinity, and I think that's the way that I'm going to encourage you to do it. But I just wanted to let you know that it does seem a little bit strange to say that it's equal to negative infinity. So just going forward, if that's something you want to think about. Next up, the limit as x approaches infinity of 5 over x. Now, this one is interesting because as this one goes out to the right-hand side of your number line, 5 stays how it is, but the denominator gets larger and larger and larger, and you take 5 divided by 10, 0.5, 5 divided by 100, 0.05, 5 divided by 1,000, 0.005. Those numbers get really, really small. Eventually, they're going to approach something that's so negligibly small that it's, you can describe it as 0. Why can you describe it as 0 if it's just negligibly small as opposed to like actually 0? Well, the problem is that there is no number that describes the value between what this approaches and 0. So if you think of a very, 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 very tiny number, 0.0 followed by a million zeros and then a 5, if we were just doing it by place values, that number's not small enough to properly represent what this is actually approaching, because there's many numbers that are smaller than that, an infinite amount of numbers that are smaller than that are between that value and 0. So no matter how small you get, you can always choose an infinite number of values that are between the one that you select and 0. So that's not really all that helpful. Why don't we just say that it approaches 0 and be done with it? So we will. So the limit as x approaches infinity of 5 over x is 0. Now, those are all well and good, and it's good to start off looking at kind of examples that look like this. But this is going to be probably more along the lines of what you would be asked to evaluate or look into when looking at these limits where it's the variable value that's approaching something that's infinite. All right, so I am going to I'm going to show you a trick that you can use to make this look a little bit different. And then after that trick, I'm going to show you another trick that kind of relies on this one that makes this really, really simple and really fast. And it should be something that you find very, very easy going forward. It will help you out a ton in our next unit, which is rational functions. Because this behavior that we're looking at right now has a lot to do with an idea called asymptotes. And we'll discuss those a little bit later on, however. All right, so the limit as x approaches negative infinity of 5x cubed minus 7x plus 1 over 2x cubed plus 6x. Whoops, minus 3. Now, I'm going to take everything and I'm going to divide it by the highest power of x. And I'm going to make some arguments as to why I'm doing that in just a moment. But let me do it first and let you see what it looks like. So if I divide absolutely everything by x cubed, or you can think about that as dividing everything in the numerator, or multiplying everything in the numerator by 1 over x cubed, and multiplying everything in the denominator by 1 over x cubed. I'm going to actually take this once and write that out so that you're fully aware that what I'm doing is okay, because this at the front, that's 1, so it's something divided by itself. But I'm going to take those two somethings and multiply them in instead. So we're going to get the limit as x approaches infinity of 5. I'm going to take this real slow this time. So 5x cubed over x cubed minus 7x over x cubed plus 1 over x cubed all over 2x cubed over x cubed plus 6x over x cubed minus 3 over x cubed. Now, from here, I'm going to actually simplify these. So this is the limit as x approaches infinity of 5 minus 7 over x squared. I'm just going to subtract the exponents or simplify that the powers that are there. X to the 1 divided by x to the 3 is x to the minus 2, or same thing as x squared in the denominator, plus 1 over x cubed, not much to do there, over 2 plus 6 over x squared minus 3 over x cubed. All right, now I'm going to actually try to evaluate the limit now. Of course, using limit properties, the limit of the quotient is the same as the limit of the numerator over the limit of the denominator. And the limit of the numerator is just these 3 pieces separated, and the limit of the denominator are these 3 pieces separated. So I can actually do each one of those pieces entirely separate according to our limit rules. So we take the limit as x approaches infinity of 5. It's 5. The limit as x approaches infinity of 7 divided by something extremely large. 7 divided by something extremely large, for the same reasons that we said on the last page, is going to be 0. 1 divided by something extremely large is 0. 2 minus 6 divided by something extremely large minus 3 divided by something extremely large is going to give us 5 over 2. And so I'm going to actually do a little thing over here where I show you this particular function. And so this is 5x cubed minus 7x plus 1 in bracket divided by 2x cubed plus 6x minus 3. Whoops. Minus 3. All right, so this is this lovely little thing that we are currently dealing with. Pretty. All right, so the what we are interested in, though, is not all this stuff. We're actually interested in what's going on way out here. Now, way out here is kind of a funny thing to say because I'm currently scrolled out to 70. Now, at 70, I'm at 2.498. That's interesting. That's really close to 5/2 already. Now, if I called this function f of x, Desmos, again, is really smart, and I can say things like f of 70. That's what I was looking at right there. But what if I said f of 7,000? Ooh, 2.4999977, or 78 if you round. That's really close to 2.5. I'm feeling like this definitely is closing in on that value of 2.5 as we go over to the right, and that's what we found algebraically too by evaluating the infinite limits. So this one's a little busier looking, but if we make it look like little pieces that are like this one not so much because that's in infinity, but if we can make it look like this or these, we're gonna have an easier time evaluating those pieces like we did on here, these yellow pieces. That's really good. So we are going to use that idea in order to come up with kind of a method or a rule of doing these a lot faster. So this first case here, that is what we just did. So I'm going to say that the reason we had things wind up the way that we did is because in the first case, the power of x that is the highest in the numerator and the power of x that is the highest in the denominator. Actually, I'm going to, because you folks are used to polynomials, I'm going to say the order. And I'm going to say that what we're doing is we're looking at the order of the numerator versus the order of the denominator. And that is the comparison that I'd like you to make when we're trying to figure out a way to do these real fast. So if we backtrack to my work here, you'll notice that the only things that mattered were the coefficients on the x cubed terms. Now, the reason why it was a ratio of 5/2 is because when we look at the little individual pieces of that top left case that's down there, that's to my right, that's so weird. So that top left case, if we were to put really big values into each one of those pieces, the cubes just dominate the other ones. So you get like 1,000,000 cubed. Who cares about 7 million when you're looking at 1,000,000 cubed? And the number 1 is not even relevant anymore. Then in the denominator, you'd have 1,000,000 cubed times 2. Now, the difference between those two is still big, but it's not, the ratio is not that big. So you get 1,000,000 cubed times 5 and 1,000,000 cubed times 2. Well, it's still 5 halves larger, the top one, than the bottom one. But that's 5 halves, not like millions upon trillions of times bigger, depending on which term you're looking at. What we're doing is we're saying this case is the special case where the order in the numerator and the order in the denominator are the same. So if that's true, then the ratio of the coefficients is the fast answer to the infinite limit. So what I would really advise you to do is try some practice problems where you do this the longer way, and then notice that pattern yourself, that the ratio of the coefficient in the numerator over the coefficient in the denominator on your highest power term is going to be the same as your answer as long as your order is the same. So in this case, cubed to cubed. This is another case, our middle one here, where we are instead saying the order in the numerator is lower than the order in the denominator. What that means is this denominator is going to whoop this numerator's butt when it comes to values. Now, so something big over something just big means that the big is, or well, 3, whatever, is going to win. It's going to be so much larger than the numerator, and it's going to get worse the further you go along. Because if you take, for instance, 2 and cube it, it's 8, and 2 and square it, it's 4. Well, 4 versus 8, who really cares? You take 1,000,000 and cube it, and you end up getting 18 zeros, and then you take 1,000,000 and square it, and you only have 12 zeros. That's 12 zeros versus 18 zeros. I mean, I'm going to just be silly for a minute. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 versus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Wow, that's those two numbers are not similar at all. So the the idea that the bottom term will continue to get more and more dominant over the top term is going to be true. And so if we did this by dividing each and everything by the highest order of x cubed, then you would get 3 over x up top minus 7 over x squared plus 5 over x cubed. Each one of those would become 0. And in the denominator, 2 over x cubed divided by x cubed gives you just 2, and then you'd get the other stuff. 0 divided by 2 gives you 0 in this case. So what we're going to find is that if the highest order is in the denominator, then it will always give you something that approaches 0. So always approaches the ratio was the first one, always approaches 0 is the second one, and in the third one, the numerator is the one that's winning. It has the highest order of x, or the highest order. So it is going to just get so extremely large that when you do the division, it's still approaching an infinitely large value. So we're going to get something like positive infinity or negative infinity, depending on the signs that are involved here. In the case that we're looking at down there, divide everything in that bottom right example by x to the 4th power. That would end up giving you 3 minus 1 over x cubed plus 2 over x to the 4. Everything up top, you get a 3, 0, 0, or minus 0 plus 0. In the denominator, that's going to be 2 divided by x squared minus 1 over x minus 3 over x to the 4, 0 minus 0 minus 0 downstairs. So you end up getting, in that case, I'll write that down, 3 over 0. Now this is very different than something that some of you have seen while playing around with the algebraic limit examples. In the algebraic limit examples, we get 0 over 0 a lot. 0 over 0 is an indeterminate form. That means we don't know what the answer is yet in the way that it looks right now. 3 over 0 is not an indeterminate form. That is a finite number 3 divided by an extremely small value, something that's approaching 0. That blows up. In this case, it blows up in a positive way because you would be getting values that are, if we look at the denominator there, it would be 2 over x to the second power, and those are going to be positive small values as we come in because we're putting a positive infinity into that. So we get 3 divided by positive very small values. So you're going to get a positive infinity as being the result of that particular division. These are pretty fun. If you do some examples, you can get so that you're really comfortable with them, and you can look at them pretty quickly and determine what the answers are to them without putting a whole lot of work into them. At first, maybe try it out a little bit, the kind of longer way like we did with this one, just to show it and be comfortable with why that's the case. But then identifying them afterwards is going to be very, very quick. All right. So I'm going to talk about the other type of limit as well. So the other type of limit is when you approach a particular value from either the left or the right, or both sides even, and what ends up happening is you get blowing up values. So it goes, you're kind of coming along, you're going do, 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 and all of a sudden it just shoots right up. And the values just get larger and larger and larger with no end in sight. They approach either positive infinity or negative infinity, and this happens at some finite value in the middle of your number line. So let's take a look at a couple examples that will do that. So if I have, for instance, 1 over x. So 1 over x, as we approach 0. So let me do it from the right. So if I said the limit 1 over x as x approaches 0 from the right, we could do things like 0.1, 0.01, and we would see that that would become 10 and 100, and it's going to be 1,000 and 10,000, and et cetera, if we just went by place values. That's going to get bigger and bigger and bigger, and there's going to be no end in sight. So what's going to happen here is that this gives us an infinitely large positive value. If we were to approach this from the other side of the number line, and then so we said, well, let's put in values like negative 0.1 and negative 0.01. We would get negative 10 and negative 100. So in this case, we're going to get negative values that are approaching an infinitely large number as well. What that means is if we wanted to state what is the limit as x approaches 0 of the overall 1 over x, that actually is just going to be, well, DNE, because we don't agree from the left and the right. Even textbooks that like saying the plus infinity and the minus infinity, you can't really say it's plus or minus infinity because that doesn't really make much sense. It's not both. It's one from one side, one from the other side. So there is no overall limit, but the individual one-sided limits could be described. If we were to take a look instead at the other function there, which is the 1 over x squared function, and do the same thing. So limit as x approaches 0 from the right, the limit as x approaches 0 from the left of 1 over x squared, 1 over x squared. In these cases, we could say, so when x is 0.1 and 0.01, then 1 over x squared is going to be 100, and 1 over x squared is going to be 10,000. And if I did the same thing down here, except for with the negative values, then we would have negative 0.1, negative 0.01, and so we get 100 and 10,000 again, because the sign goes away in the squaring. So we actually get positive infinity for that one and positive infinity for that one. So it would be entirely okay, because the two one-sided limits agree with each other, to say that the overall limit is going to also be positive infinity. So that's all I'll really say about that type of limit. Generally, it's going to be seen as, again, there's going to be a funny word called asymptote that comes into play in the next section, and we'll talk about them a little bit more there. But just in terms of evaluating them, for the time being, you're going to see things that turn out being some number divided by something that approaches 0. And depending on whether you have an overall positive or overall negative to that division, you're going to say that it approaches positive infinity or negative infinity. So that's good for now. And if you would like to do a little bit of practice there, that's great. And I hope you're doing well, and take care.